the problem statement asks us to connect two loads, one light, green, and one heavy. We will swing over the horizontal rod. Upon release from the given position, we can observe looping of the load around the rod that prevents the heavy load from falling. We should investigate this phenomenon. The most relevant parameters are mass ratio, rope length, and the release angle of the light load. So, our apparatus consists of two stands. On one is a horizontal rod, of which a heavy load is suspended. The second stand is used to fix the light load and the angle of its release. We use the projector to ensure constant angle of release and meter to set rope length in our measurements. This is how the phenomenon looks like. The rate will slow down so we can appreciate the spiral trajectory of the light load. Well, why does it loop? Intuitively, we would expect the light load, when released, to behave as a pendulum and fall on a curve the trajectory due to the sum of the gravitational and tension forces. However, during the fall of the light load, as it turns around the horizontal rod, the thread itself shortens. That means that during the first phase of the movement, as the light load accelerates, it has greater thread to swing with, and therefore it accelerates more than it decelerates coming up. This creates, this ensures that the vertical component of velocity is non-zero in the after 180 swing. Well, we define. We need to ask ourselves how we can interpret our experiments. When we define our experiments, the most relevant parameters, as I said, are mass ratio, release angle, and rope length. And we define a measurable variable epsilon, which is defined as such, as the length of the rope that looped around the rod. This is how the mass ratio affects the relative term. We can see that with really small mass ratio, epsilon is small. In this region, we do observe different regimes, which we will come back to in the end of the presentation. At the border of these regimes, we obtain maximum relative turn. There is a maximum possible mass ratio for the phenomenon occur in this setting. Here we can see from the 90 degree at around 50. With greater mass ratio, friction is not able to compensate gravitational force of the heavy load, and such it falls down. We repeated this experiment for two release angles. Further, we observed increasing relative turn with decreasing angle of release, as the small load has greater initial potential energy and can therefore swing further and faster around the rod. So, next, we change the friction coefficient of our rod. We can see that with greater friction, as the orange dots are the friction, we are pushed upwards in the relative turn. This is because with greater friction, less angle is needed less turn is needed for the load to stop, and therefore it can swing further. The rest of the thread itself swings around the rod and we have a great relative turn. Now we can come to our theoretical approach. As the light load turns around the rod, we see a decrease in tension of the thread because of the friction. This is defined by a simple Kaplan equation that is derived in the appendix. And now we can and we see that the tension drop decreases exponentially with the turn angle. Now let's take a look at our exact theoretical model. We assumed the following, the most important of which is that the mass of the rope is neglected, and that the elastic collision between light load and the rod are, the collisions between light load and the rod are elastic. We can describe the whole system at any moment by the position of the two loads. Heavy load moves only in y direction, and we describe the light load by its polar coordinates L and theta. To elegantly describe our system, we have to take a step back from the Newtonian mechanics and look at the problem from the point of view of energies. So we write down our Lagrangian, where this part comes from the kinetic energy of the system, and this from the potential. And this corresponds to the heavy load, and this is for the light load. Using Euler-Lagrange equation, where the friction and the Kaplan equation is put into the Lagrange multiplier, and using the conservative equation of the condition of non-expansion of the rope, we can obtain equations of motion, where the friction is calculated with the tension. Explicit form is in the appendix. This is all we need for the numerical simulation. So, we create our numerical simulation, and this is the typical outcome. We can see qualitatively that it behaves similarly. So, we have other qualitative comparison, and we cannot only compare the trajectory qualitatively, but also quantitatively. We can see that we can see almost perfect correlation. However, as we did not calculate air drag into the equation, we see that the simulation slightly runs forward from the experiment. Further, we can take a look at the dependencies that we measured. This is the dependency of the relative turn on the mass ratio. For a small ratio of the rope, for the small ratio, the mass of the rope is compared to the small load, and so we can cannot neglect it as the theory expects us to, and therefore it doesn't add up. With the increasing angle of release, we see that we obtain an angle where it doesn't move, as it does not have enough energy to swing to the opposite direction through the rope, and it compares fairly well. Nextly, we can compare our dependencies measured with different friction coefficients, and we see that that it compares fairly well. However, there are some discrepancies that the theory overpredicts the experiments a bit due to we believe air drag that was not calculated in the theory. Now, we can take a look at the different regimes that occur in the system. So, again, this is the first regime, the looping, and we can compare it, and we can plot a phase diagram. Where do we observe the loop? In the these are the crosses are the experiments, and the regions are from the simulation. We can see that as we increase the length of the rope, we obtain more of the successful looping. The further additional regime is the regime D1, the heavy load stops due to the centrifugal acceleration of the small load, and the small one starts to loop. This causes it to lose velocity. It causes it to lose the velocity, and tension in the rope decreases. Decrease of tension decreases friction as well, and the heavy load starts to fall again. However, only for a short while, as the small load loops around and friction causes the heavy load to stop again. And we can again plot it on our phase diagram, and we see it at a relatively small mass ratios. Next one is the regime D1. It is similar to the regime D2. It is similar to regime D1. However, during the second phase of movement, the heavy load is small, pulled from under the rod, not up, and that's why it loops from the other side. In the experiment, we observe two possible situations. The small load either simply unwinds and the system falls, as is shown on simulation and in the video. The other one is that it loops due to the horizontal direction of the movement, as is seen on the right-hand side. We decided to combine regime D1 and D2 in theoretical prediction, as our simulation does not predict the looping and staying, not falling of the D2. Next is the pendulum regime. With pendulum regime located on the left of the diagram, we finish the phase diagram of the system. And the pendulum regime occurs due to the small mass ratio around 1, and gravitational work acting on heavy load does not compensate tension from the small load until the small load stops moving. That occurs at the point of maximum deviation. So we plot it, and we finish our phase diagram. To create our phase diagram, we did over 1,000 experiments and countless simulations.
Okay, nice, it's over.
Thank you.
Thank you, Mr. That was an outstanding presentation. However, could you please go to page 33?
Page
33. Okay, so this is the rod that you are using throughout every experiment, right?
Yes?
Okay, thank you. And you also
Well,
have...
what do with the different frictions?
Okay, this?
When we change frictions, or we change the same paper?
Okay, so you not change the bar, but you change the rope. So when you change friction, you change the bar or the rope?
We added sandpaper on the rope.
And can you can you show the derivation of your capstan equation?
Derivation?
The derivation of the capstan friction. Okay. Okay, thank you. And how did you measure the friction coefficient?
We measured two types of friction. We measured static friction of our experiments as such. We turned it around the rod and we pulled it. We measured the force, and we measured the sliding friction as we turned it, let the system fall, and measured the acceleration. Afterward, we fitted the accelerations from this equation for the friction
Okay,
coefficient.
have you purposely on purpose pull the light load onto the side such that the light load wouldn't hit the rope?
Yes, in our experiments we did pull it to the side,
Okay,
but we did not further investigate.
and did you take that into account in the simulation?
No.
Okay, thank you. And what can you show? Are there any more graphs where you fit your trajectory of the where you fit the real trajectory with the simulation trajectory?
Trajectory of the
Yeah, you only show us one graph and show any more.
Yes, we can in discussion probably.
Okay, thank you.
Thank you. It's time for preparation.
Okay, good morning everyone. I am Sri Prasivanna, a representative from Thailand. With you, of course, the question of looping pendulum. So, for the problem statement, connect two loads, one heavy and one light, with a spring over a horizontal rod and lift up the heavy load by pulling down the light one, release the light load, and will swing around the rod, keeping the heavy load from falling to the ground. Investigate this phenomenon. So for the completion of tasks, I give them actually to fulfill because there are some misassumption of this. theory I will discuss later, and there are some graphs that they have not yet shown whether that theory is possible or not. And for the reported outline, they began by introducing us with the phenomenon video and explanation of the phenomenon qualitatively. And for the theoretical part, they say that thread gets shorter during the deceleration, causing the vertical velocity to be non-zero. And Cartesian coordinate forces are considered for the heavy load, and rotational coordinates are for light load. Stopping heavy load from using the stopping of the heavy load was caused by the friction from the Kaplan equation and the water loss from the light load, and solving the equation of motion using Euler-Lagrange equation with the friction term. And for the free estimate, they define new variable friction of both plate contraction. And for the experimental part, they check the mass ratio, angle of release, vary friction coefficient, and on the fourth experiment, they simulation of friction compared to experiment, and they calculate the phase diagram of the last experiment. Okay, so on the strength and weakness of the reporter, they have good visualization and problem analysis, and they have variety of parameters that are relevant are investigated. Problem was investigated in many aspects. However, the setup was not carefully controlled, which I will discuss later on the discussion part. They did not mention about the origin of friction term in Lagrange equation, and the measurement method of the friction coefficient was not mentioned until I clarified. And the friction coefficient in capstan was not identified. And for the next one. Okay, so for the positive type, first we will discuss the capstan equation derivation with is it true to be assumed in this phenomenon, and as you also ask whether there are three parameters during the fitting and the experiment and measurement, and will ask about the control acting tape over the rod and 3D movement as they have to light load onto the side to purposely make the phenomenon successful. And for the result, I will discuss on some unfit theoretical graph line with the result, and can I invite the presenter to the stage to discuss. Okay, can you please turn to the page where you divide the capstan equation? Yeah. Okay, yeah, so x direction is on this direction, am I correct?
Again?
So for the x direction force, this is on this parallel to the surface.
Yeah, I believe so.
Okay, yes, but however, well, that's the globe. So you use capstan equation even when rope is moving and accelerating, right?
Well, we believe it is in our experiment. It is a good approximation. As we use a sliding friction coefficient, we are aware that the capstan equation is derived for the stationary situation, but we find a good approximation in our theory.
Okay, so
as it works.
So what I can tell you for when rope is moving, though it should have some term that is concerning rope acceleration, but so you neglect it, but it's quite good approximation, correct?
Yes.
Okay, that's why we missed that on that part because they also neglect the rope mass, which would be added for some terms. But however, so we clear on this part where the rope accelerate and they use new A instead of new static. And
we use
and on the next part where rope is not sliding, but the tension, so this one, T1 and T2. When rope is not sliding, I think the tension of this part does not have to be on, sorry, I'm wrong one. Does not have to be on this side. So what I'm saying here is that for the condition of capstan equation, it is about to slip. That means it's using the maximum static friction. But during the stop of the simulation, the smooth static does not have to be on its full friction. Do you understand?
I'm not sure. I'm probably going to answer. Our simulation calculates the sliding friction. When this friction force compensates the gravitational pull of the heavy load, the simulation stops. Afterwards, the light load swings further, and after it stops, the static friction applies, but we don't have to actually care about the static friction because it already stopped.
Then are there any regime where it's like it stopped one and it's actually accelerate again and it's fall apart?
Yes.
Fall how can you simulate that? If you say with static friction is one acting, it will stop completely and it will not move again.
I said that we calculate the sliding friction
Okay.
during the swinging,
Okay. Yes.
and when the heavy load stops, we put there the static friction afterwards when it stopped, and when it stopped, if the static friction does not compensate the heavy load, then then it starts to fall again, and then we put the static sliding friction again.
Okay. So.
Are we clear?
Oh yeah. So. Are there any collision where the screw slip on the light load side where the heavy load is pulled? Was not just stop and it was pulled.
Heavy load is pulled?
Yes, instead of stopping, this thing accelerates. So have so much tension, it can actually pull down.
Yes, it can happen.
So can you write the condition where the friction will like the inequalities or equation that can satisfy this friction? Like what would be the condition for this to apply?
A condition, okay.
Yes.
The condition for this to apply, well, the force created by the light load, the tension must be greater than the created by the heavy load. It happens when the mass ratios are similar, around 1. When the masses are similar at around 1. So therefore, when the light load accelerates, it creates a greater pull on the thread, and so the Kaplan equation switches. So this is then T1, here is T1, and here is T2.
Okay, so how do you switch the Kaplan equation? Because in this case, let's say T1 equal to this and T2 equal to this, it would be some kind of discrete curve where this one is E mu, and then you switch time into this E to power mu x. Do you think that any mechanical system has some kind of like very discrete movement?
I do not follow.
Well, let's say this one is n. Are there any examples where these two is equal?
For these two equal?
Yes.
Well, it should be for as it slides, it should be less than or greater than. And I'm sorry, I'm a bit lost. In our simulation, what we did, we created a condition. We did not analytically solve this condition where it switches. We put a condition when this pull is greater, the Kaplan equation switches, so it can be pulled up.
Okay, thank you. I think you have got quite good understanding of Kaplan equation.
Okay.
So, but let's move on to another assumption. Well, the rod which you were using was braided and correct. Again, was some kind. Can you show slide number 30? I guess where is it show at the rope. No, but sometimes like where you show the rope. The rope? Yeah, the rope. That's the rope. Look like. Oh yeah, so as you can see here, your rope was not smooth.
Yes, it wasn't smooth.
Well, now Kaplan equation, because doing a Kaplan derivation you have to integrate. But however, this contacting is not continuous and actually discrete. Would this break down your Kaplan equation?
Well, we used a Kaplan equation to simulate the sliding friction. But this is like a second order approximation, like second order effect that we did not put into consideration, but it still compares fairly well.
Well, how about you change your type of rope doing experiments to something like nylon string where it's actually smooth and would actually satisfy the Kaplan equation more? You know nylon string?
Yes, I understand. Yes.
So okay, so in this
there is not such a significant effect that would be such an important effect.
okay, thank you for this discussion point. We both agree that the rope, but it should have some effect. But however, we disagree on that. They stated that it would not have much effect. However, I think they should have used some kind of smooth rope, such as nylon string, so that it can satisfy the Kaplan equation. And can you go to and you doing the friction checking? When you added the tape over the rod with the sandpaper.
Yes.
And sandpaper is actually rough, and that means at any point of the sandpaper it would not have the same friction because it's actually not that measurable?
Well, we measured the friction coefficient from the whole friction coefficient. We created experiments where we measured the friction coefficient of our rods and of our sandpapers.
How many
And there
times
is
did
an
you
effective friction coefficient.
So how many times did you repeat this?
I mean,
There are no error bars, so we cannot know whether it's repeated or not.
this is just example how was one knee fitted, and we created it. We did the experiment a few times. I mean, like 5 or some, and we fitted it. We took the parameter and averaged the parameter, and there weren't significant discrepancies.
Okay, thank you. And also you mentioned that you pull the light load onto the side, right? Slightly bent so it wouldn't hit the wall on purpose.
Yes.
Wouldn't that affect your whole process system as it would affect the tension, the capstan equation, and it's slightly bent on the tension, and it's also affect your configuration?
I mean, of course, if you pull it to the side, if you want to investigate the horizontal movement,
Then have you
there
control
is
the
an
angle?
effect.
Have you can control the angle where you pull it to the side?
Yes, we can.
How do you measure it?
We moved it to the side the smallest amount possible for the
How small in degree or radian?
for the heavy load and light load not to collide.
Okay.
That depends with the length of the rope at a few degrees.
Thank you. But however, I think you should actually improve one of the control parameter and control it properly, like some kind of 3 degree or some like new number, so that we can maybe you can use it to investigate more on the 3-dimensional movement. And can you also are there any fitting or free parameter in your numerical simulation?
No.
Okay, thank you. And for the unfit theory, can you go to any part of this, any graphics in the phase diagram? Okay, well, do you think that, well, are there any, well, so other than the airbag, because I think airbag only affect mostly on the second phase, right? That is, the world like spin very fast.
Well, yeah.
Okay, so this is mostly depending on the first phase, where the work is sliding, right?
Well, this theory experiment comparison is when we take the when we take our rod, let the thread fall down, and it swings, and when it stops, it swings further,
So
and we measure the ratio of the swing thread to the whole thread.
So it's still depend on this part, right? When it stops, it's stop, right?
Yeah.
Okay, so what do you think are something that is affecting your brain? Do you think it is the source of the error in this case?
I believe that the one source of the error is the air drag,
Okay,
and the
thank
further source of the error might be the on this side might be that the mass ratio is too small and the rope itself has an effect.
Okay,
thank you.
Also, to summarize our discussion, so the first topic is the Kaplan equation. Also, the opponent explained how they derive the Kaplan equation. However, we suggest the Kaplan equation have to be modified to account for the mass of the rope, or maybe add some term, or clarify it clearly during the presentation. And for the second discussion, the smoothness of the rope, would it affect the Kaplan equation? The reporter agreed with us that it would affect the Kaplan equation. However, they say that its error is small. But however, I think they should change the type of rope to satisfy this equation. So the third discussion, how did the reporter measure the friction? It is the reporter state that they measure the friction repeatedly, which is a good thing. And for the fourth discussion, horizontal angle during the division, would it deviate the theory? Reporter says did not control but assumed to be negligible, but however, I think it should be a control parameter and consider it in discussion. And on the last discussion, why that the data on the bar does not fit the graph. A reporter says some kind of airbag, but however, I think it should do the formula in Newtonian mechanics so it can include in airbag.
Okay, thank you. It's time for the review questions.
Hello, within the reporter and the opponent discussion. So, in which angle is the gravitational torque the maximum?
Gravitational torque.
Yeah.
At the release.
In which angle?
Well, the gravitational torque is
Give me a number,
well, when I release it, because as it falls down, the thread shortens,
So which
so the
angle?
arc shortens, so the torque is greatest upon
Which
release.
angle?
The release angle.
Yeah, depending when you release that, in which angle you release that. To the opponent?
Half a pi, I mean 90 degrees.
Okay. How many different tests did you conduct using different masses?
Again,
How many tests did you conduct using different size masses?
different size masses. We conducted here. There are different mass ratios, and each dot is consisted of, I believe, 6 measurements.
Throughout the whole experiment, is the angular acceleration positive?
Again,
Is the angular acceleration positive?
is the angular acceleration positive? Well, it depends on how you define the positive. It is the same. Well,
Okay.
as we do not expect it to collide.
Does the momentum of the system stay the same?
Does the momentum of the system stay the same? Well, there's friction, so it stops. So
To the opponent?
I agree with you part on this one.
What should be the ideal analogy of the masses in order for the looping pendulum to happen?
could you repeat the question?
What should be the ideal analogy of the masses in order for the looping pendulum to happen?
In order for looping pendulum to happen, in our phase diagram we see that the looping occurs across different mass ratios and depends on the mass ratio and the length of the rope that you use.
How do you measure the friction between the string and the jellies?
The string and the rod. You mean?
Yeah.
Okay. We measured it 2 ways. We measured the static friction when we pulled the weight turned around the rod with a Newton meter, and the sliding friction we measured when we measured the acceleration of the whole system, and we fitted the friction coefficient.
The last question, what does the derivative Q mean in your slide 20?
Again?
Slide 20, what does the derivative Q mean?
Derivative Q, position.
Thank you very much.
Parameterized position.
Okay, thank you. Let's proceed.
Once again, we thank the opponent for the whole discussion and analysis. Let's proceed with our review. First of all, let's restate the problem that let's suppose that we investigate. So, coming to road from having a line with a string over a horizontal road and lift up the heavy load by pulling down the light. Release the light load and it will sweep around the road, keeping the heavy load from falling to the ground. Investigate this phenomenon. Now, about the reporter, there are some strong points. Interactive images were presented in the theoretical explanation with graphs, analysis about masses. There was also analysis of forces acting on the object. Refer to special regimes and for change the mass ratio. However, there were some weaknesses. When I asked the reporter to comment on the momentum of the system, whether it does stay the same, he didn't have the comment. He didn't have any comment. Also, didn't explain the mathematical formulas as I asked before and the conclusions that he reached. Also didn't take into account the air drag in the whole experiment. There was not any reference to whether, what's first of all the mathematical type of the air drag and whether that affects the whole experiment and in which ways does that affect that. Also, he manages his time effectively. He spent a lot of time analyzing the theoretical part, whereas he should emphasize more on the graphs and an analytical explanation of the schemes. And also the structure of the presentation. About the opponent, he summarized the reporter's presentation accurately, challenged the reporter in multiple aspects of this presentation, pointing out some minor mistakes and facts that were omitted from the reporter's presentation. He tackled also some parts about the graphs that the reporter didn't mention adequately and early. However, there were some weaknesses too. Didn't take full advantage of the given time in the presentation of the reporter. There was the weak prioritization, and he didn't use the time effectively in some cases. When he could like spend time analyzing or asking the reporter about the graphs. Now, about some class points, the opponent, static friction should be considered. The reporter says when the load stops, it's not necessary. Opponent, even then, the mass can acquire acceleration. Our opinion, theoretical model that concludes that friction should be developed in order to study the behavior of the mass. Another class point is, what's the mass ratio? The reporter, it said it's approximately 1, when in fact there was some analysis regarding that. Where it states that it's different, and Discussion he said something else. Our opinion in order to investigate phenomenon of the mass should be around 1/6 to 14 times. Another class point opponent will let the light load go from a small angle so that it does not collide with a heavy load reporter. This would be a significant factor for phenomenon. And our opinion, it is acceptable to light it from a small angle as long as there is a proper mathematical model to account for. And the conclusions are...
Okay, thank you, time is over. Okay, the next part. It's time for you.
Well, first of all, I would like to thank the opponent for the discussion and review for the review. I would like to state my some things to the points of the review and the opposition. Through the 3D motion, and the release angle, horizontal release angle, we used a small horizontal release angle, and upon using such small angles, all the terms if we were to calculate in the horizontal plane, movement in the horizontal plane, would go to 0. And further, in the discussion we clarified the misconceptions and the use of the Kaplan equation in our presentation. We went through a few other misconceptions with the thread. We believe that the thread itself, the bumpiness of the thread is not such an important effect in this phenomenon, and it will not create such significant discrepancies that we need to consider it. Further, I would like to thank you all for your time.
It's time for the jury question. Okay, please.
Question for the reviewer. You said was the angular acceleration positive? Can you tell me what you thought, please?
Yeah, I asked whether it's always positive, and my comment on this is that it does not stay positive based on the gravitational torque that is exerted on the light object, and depending on which angle it is, whether it's like from this area or this area, it changes. So it sweeps from sometimes it's positive and some other times it's negative.
Thank you.
Okay, thank you. Further questions?
The reporter, you talked about in slide 12 about it being an elastic collision. Oh, sorry, slide 18. Could you tell me what you meant by that?
Slide
18, I think.
when the light load hits the rod, it's deflected. It collides and it pushes back and it unwinds. So in our theoretical model, we assume that all energy is transferred into the rod, and therefore the experiment stops at the and how we then put this into our experiment is that we caught the light load as it stopped and checked if it falls down.
Okay.
So my question is to the opponent. So if you would like to improve that theory, what would be your next step?
Okay, first thing, there are two things to improve. The first one being the Kaplan equation. So to concern about it, Kaplan equation, first it will be
Only a short answer, please. So what is the phenomenon which we would like to...
Kaplan include the term of mass and body. Three-dimensional,
Okay, thanks. And the reviewer?
How could you improve that in the problem?
What would be the next step? Okay. Next step, if you would like to improve. So what other phenomena should be?
What would be the next step? First of all, to take into consideration some parts that are important miss, like the head drag.
Okay. And
Well, we would calculate the mass of the rod at the movement.
oh, okay, thanks.
And
Okay.
put down the assumptions.
Yes.
For the phase diagram, you've considered the rod, and then you have considered higher friction. Now, if you had much lower friction, would there be any major changes to this phase diagram?
To this
Will there
phase
be new
diagram?
regimes?
To this phase diagram with the lower friction, we would see it pulling to this side, to the right hand side. So the regions would go there. So here's experimental phase diagram with the lower friction, and we see that it
Higher friction, is it?
the higher friction. Okay.
And the lower friction, what would happen?
The lower friction. I'm sorry, there must be a mistake on this slide. This is for the lower friction.
Okay.
What about for the reviewer and the opponent? Will there be any new regimes? Will you actually see any new regimes? Or they have covered everything already?
I think if they don't consider the fact that light load can hit the rope, they can call it regimes.
May I state to the different regimes? We could see a different regimes, like, but only D1 and D2 regimes. Like it swings a few times and then it turns, and more times and then it turns.
And then I also would like to ask about this diagram. When you go to the higher ratio, you see quite a disagreement between expectations and measurements.
Yes.
Yeah. Can you comment on that? I mean, those green part that enters the network over here?
These few points
Yeah.
here.
Can you comment on that?
Okay.
What was the main cause of that disagreement?
What is the main cause of this disagreement? Well, we could say it would be, it could be, an interesting point. It could be, nothing comes to mind.
Okay. Any of you can comment on that?
To me, it could seem like the statistical error that happened because that failed and successful. Depending what you actually done, but as I see that without.
Okay, now it's over. We need some moments for the grading. Thank you so much again. Scores for the reporter. It's 7, 8, 9, 7, and 7. Grades for the opponent. It's like 6, 7, 7, 6, and 5. Sorry for reading the opposite way. And finally, for the reviewer, this time I do it right. So it's 4, 4, 5, 4, and 5. Thank you so much. And let's comment on that. May I have okay, Gabor, what's your mark for the opponent? What was your mark for the opponent? 6. It was 6. Okay. Sorry, that was my fault. Okay, here we are. Let's start with the reporter. And it looks like we have 7s and 4 here. So let's start with 7. For the reporter. So 7 is the lowest one. And I gave 7. Maybe I can comment on that. This lower mark in comparison to my colleagues is due to mostly to a time management. And actually, I really like your presentation. It has a different structure, let's say a bit different structure what was pointed by the reviewer, but it was really clear. And then this time that you will really need is the time for a conclusion. And if you conclude this, it will make your presentation even better. So this is why I act in a way that I gave you 7, which is still quite a lot. And it's also, you know, I asked you this final question, which I thought that you will come up, you know, immediately with the solution, because it was really soft on that. But you did not. So, and I also have to comment that I did not really appreciate the comment of the reviewer, because in my opinion it's not the matter of the uncertainty. It's something which has to do with the aircraft. You were talking about this, so it could really be a reason for that. Yeah, you just say it so. Okay, and I will ask Zachar to comment his 9.
No, I gave it.
8, but
I gave it 9. Oh.
So it looks like, yeah, you gave.
I gave an 8. I gave a 9.
Now have a look here.
We have problem with the
Yeah, because we have it.
Okay, I think
The thing is, you two sit different.
Okay, so yeah, we will clear this up after the fight. So let ask Paul to comment his 9.
Okay. Yeah, I thought it was a very well done project. You've done a lot of work on this to come up with that phase diagram. I can see so many points, so I think that's something to be commended. It's the best presentation I've seen so far, and I gave an 8 yesterday, so I think I have to give something better today.
Okay, any further comments? Yeah, of course.
Well, so indeed it was a very nice presentation and a very full solution, and I was very pleased to see that. The only thing which I could add to this was to do some theoretical, analytical results. So you put that to do that with your theory, and everything else was very nice. And you could be a little more confident on that. So you have a very nice solution. So
okay, I think we should proceed to opponent. And again, we have some 7s and 1 5 here. So let's start with 7. Maybe Susan, this time you can comment your 7 on the opponent.
I thought you spent too long, unfortunately, on the Capstan equation. I felt that it was not covering a whole presentation, and I think that was the main reason I gave it a lower mark than I might have otherwise.
And actually, that was about what I would like to say about my 5, because you really spent the majority of time on that, and you did not really comment on other things that were listed on your points for the discussion, and even more, the prioritization of your talk was also something, in my opinion, that needs to be improved. And then also, when you should spend more time on talking about other aspects of this theory and comment on this huge range of the mass ratio that was investigated. And during the report, the presentation of the number of experiments conducted was also huge, and you did not really take this into account. And of course, there were also some things to improve. For example, they did not change the radius of row, and it might also have some influence on that, and you did not even come up with this idea. So this is why I gave you 5. Any further comments on the opponent? If not, we can proceed to a reviewer, and we have quite an agreement here, 4 and 5. So maybe Paul, can you comment on 4?
I gave a 5.
Okay. Yeah, you're right. Yeah, you gave 4.
Okay, for the review, what was the most misunderstood for me was your opinion about the discussion points and this and the opposition, and so that was the major problem with it. I also substituted subtracted some points for the answers. I guess it's about this problem with the mass ratio that you said about the 1 in your clash points. So that was yeah. I think yes. So that was not the case, I think, which you could establish.
So Gabo, maybe you can comment on your 5.
Okay, so I agree with you. I also have some problem with your question. So I think you didn't verifying the points of report or the discussion. You only check the basic knowledge of the reporter and like an exam. So I think the most question was irrelevant.
Okay, so thank you so much again. And then we will make a 5-minute break right now. So be aware that we are meeting at 9.